Hello and welcome to this video. Today we'll explore how to analyze logs using the LogDelta tool. Part 1. Setup and high-level visual analysis. For this demonstration we are using data derived from two notable papers. The original dataset comes from the 2016 paper Log Clustering-Based Problem Identification for Online Service Systems. This data has since been republished as part of the LogHub log data collection set, making it widely accessible for research and experimentation. In this video, we'll focus exclusively on the PageRank application from the dataset. While the dataset also includes a separate application, word count, that could be analyzed in a similar manner, we will leave that for a potential future investigation. To get started, we'll set up LogDelta for our analysis. The first step is to install LogDelta using pip. Next, clone the LogDelta repository from GitHub. After cloning the repository, navigate to the LogDelta/demo/label investigation folder. Finally, download the Hadoop dataset and extract its contents into the Hadoop folder. With these steps completed, we're ready to dive into the analysis. The Hadoop dataset is organized so that each run is stored in its own folder, titled with the text application followed by an ID number. Labels for the different runs are provided in a separate file. This file maps each run ID to its corresponding label. To make this analysis compatible with LogDelta's philosophy, we need to rename the existing runs or folders using these label names. To assist with this, we provide a script that automates the renaming process, ensuring the labels are associated with each run. This makes the analysis phase easier to follow. This is the highest level analysis and is specified in the file visfilenames.yml. To generate the results, execute the script using the command python -m logdelta.config runner-c1_visfilenames.yml. The output will be saved in the out1 folder. A simple plot displays the runs with two axes, the number of log lines on the y-axis and the number of unique file names on the x-axis. The number of log lines in a run can be useful, as anomalous runs can be smaller or larger compared to normal runs. For example, a paper by Landauer et al. Demonstrated that 1/3 of anomaly log sequences in the HDFS dataset can be identified simply by their length, as they are shorter than any of the normal runs. For visualization, it's helpful to toggle runs of interest on and off. This makes them blink, making it easier to locate them on the screen. For our Hadoop dataset, we can observe on the y-axis that normal executions have a maximum of roughly 3,000 log lines. Additionally, the number of unique log file names shown on the x-axis can be particularly useful for analyzing large applications that produce multiple log files. Anomalous conditions might exhibit a larger or smaller number of unique log files compared to normal runs. In our case, normal executions have a maximum of 15 unique log files. Based on this straightforward analysis, we can define boundaries to classify anomalies. Specifically, any run with more than 15 files or more than 3,000 log lines would be considered anomalous. From the dataset, we have 29 runs in total, 8 of which are labeled as normal. When we zoom into the defined boundaries, we find 13 runs within the box, 5 labeled as anomalies and the remaining 8 as normal. This simple approach achieves a roughly 76% accuracy in identifying anomalies, successfully detecting 16 out of 21 anomalies.